So, welcome students in this new lecture in the series of lectures that we are conducting regarding geometry for IOQM. Today we have discussed some today we will be discussing some important theorems related to triangles and quadrilaterals. We have already gone through triangles, similarity, congruency, quadrilaterals, angles, parallelism. So, we have discussed these things. Now, we move on to some notions that are known to us based on notions that are known to us based on what we have gone through. Pythagoras theorem we have gone through. So, different things that we have gone through, we are now going to as such say we are now going to apply those things to come up with theorems that we are going to use in solving problems. Some of the things that we did earlier helped us in solving few problems, because in a time bound examinations certain things need to be known. As I have repeatedly kept on saying that whatever theorems you know, it is necessary that you know their proofs. Okay. So, one very important theorem that is used is, say, is Stewart's theorem. We will also go through Ceva's theorem and Menelaus theorem today, okay? And then we will see how we will apply in problem solving insofar as triangles and quadrilaterals are concerned. Primarily this is related to Stewart's. These theorems as such are related to triangles only, okay? Now, in a triangle ABC, suppose you draw a transversal from A to meet side BC at D. If these lengths are MN, this length is D, this is C and this is B. So, Stewart theorem states that and so this side is A. What does the theorem states? It is generally remembered as MAN, M-A-N, plus DAD, okay, bomb, B-M-B, bomb sink, C-N-C. So, actually it is A-M-N plus AD square is MB square plus NC square. Okay. These theorems indicate that we will be using Pythagoras theorem to prove it. How do we prove it? We draw an altitude from A. Suppose say this length is x, say A, B, C, D, say this is some M. So, let this be some P. So, this is x, this would be N minus x. Okay. So, what all we have in triangle, suppose APD we have see AP square, if we write from here is B square plus N minus x whole square. Sorry, 8. Oh, D square, very sorry. D square is AP square plus x square. We can also say B square is AP square plus N minus x whole square. Now, if we take this triangle, we have C square is equal to, what is C square? AP square plus, what do we have? M plus X whole square. So you can see, how do you get to this AD square? How will we get NC square MN square? So you can say this, you multiply this by A. Then you have MB square. And then you have NC square. M plus N everybody knows is A. So suppose this is 1, this is 2 and this is 3. So we have to get rid of AP and X. So one can very easily see, what do we do? 3 what will you get? NC square minus AD. So you can very easily see M plus N AP square minus AP. This will get cancelled out. What you are going to get is AMN. Okay. What you are going to get is, see, M square N plus N square N. See, M square N two MNX minus 2 MNX, that gets cancelled out. And NX square plus MX square minus AX square, that gets cancelled out. This you can write as Mn into M plus N, which is A. So AD square goes that side and you get the Stewart theorem. A very useful theorem, especially because not every time we will be having so much time that we are able to apply the theorem. So please remember this, it is something that is used especially when some lengths are given, some lengths are provided. For example, you have to find length of a median given sides of a triangle. This is a D is the unknown, everything else is known. A fantastic way. And with median, the theorem is called Apollonius theorem. What will we get for a median? You can just see. If we are drawing a median, this is A, B, C. Okay, these two are equal. Okay, so here your M is BD, N is CD, so both are equal, that is a separate issue. Okay, this is your AC, this is what you need, and as always C is AB. So MAN, what do you get? MAN, BD, A is BC, N, which is CD, plus AD square is BMB, BMB. CNC. CD into AB. So now BD and CD are all equal. So you can see BD, sorry, this was BC, BC was 2BD, MAN plus DAD. So BD, 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 CD and BDI. What is BC? BC is nothing but 2BD. Okay, so you can say 2 times, this is 2BD, this is also BD, so 2 times BD square plus AD square is equal to okay. This is called Apollonius theorem. Fine, in fact this is giving you the length of median. Okay, what will be the length of median? You can very easily see D square, let me write AD as D square, which is AC square, AC square is B square plus AB square, AB square is minus, what do you get? 2 BD square, that means so this is length of the median. So on occasions, if somebody gives you 2 sides and the median, you can find this. If somebody is asked, suppose these two lengths are given, these two lengths are given, this is given. So it is very useful when you know, because see in the proof we drew an alternative. It will not always be possible to do it literally every time. So it is advisable that you remember this, so that when such lengths are concerned, we are able to solve it. Okay. Now suppose ABC is a triangle and this is an angle bisector. These lengths as always are M and CB. Okay. If you want, because and suppose this is D. So if you want to find the length of angle bisector in terms of this, now we recall, if you remember, I hope you remember, we have already gone through this, M by N is C by B, okay, and B plus C is, and C, M plus N is A. So you can see M plus N so N is AB upon B plus C. So N is AB upon B plus C. And what is M? You can very easily say AC upon B plus C. From this we can find, and the thing that you must remember is that D square plus Mn is equal to BC, relating to, So d square is if you want to find the length BC minus Mn, M and N we are able to write like this. How do we get to it? I think we can apply again. You can see what you will write is Mn into M plus N plus D AD square MB square plus NC square. Now we know M and N. M plus N is of course A. So you have A into Mn plus D square. What do we get? M AC upon B plus C plus so A gets cancelled out. What you are left with is BC into B plus C upon B plus C. So Mn plus D square is BC. Okay. So related to angle bisectors, this needs to be kept in mind. Okay, see, finding the length will be an issue. See, as we move on, you see finding angles is generally demanding, but demanding intellectually. But if you want to find length associated, then it is generally an exercise, a laborious exercise. And for length, the theorem that we have, either we use similarity or we apply Pythagoras theorem. Just we are constantly expanding the horizon, and therefore in case you have to calculate length, it is definitely useful, it is of great help that you remember these things. So in this is, I would say, this will be the sum total of angle bisector theorem. Bisector divides the opposite side in the ratio of sides containing the angle, and so this gives you the length of angle bisector, and this gives you the length of median. See, an explicit expression here will not be great. You can see if you write Mn, what it will be. In trigonometry, you do get a reasonable expression. If you write d square is BC minus Mn. What is Mn? You can write A square BC upon B plus C whole to B square not a very viable thing to remember, okay. B plus C whole square, sorry. B plus C plus A, B plus C minus A, you can use as S minus C A type thing, but it is not a very good expression. I think this is something that we can remember. Is it not? This is something that we can very easily remember. Okay. Now you can see what sort of problems could be countered using Stewart's theorem. Now let me take a very simple problem. A very simple problem is two sides are, say, 4, 9 are two sides of a triangle. One of the sides is 6. One of the medians from vertex is 6. Okay. Somebody says find Somebody says find BC. Somebody may ask you length of other medians. Okay. So what we have just read, 2 times BD square plus AD square is AB square plus AC square. So 2x square is 81 plus 81 minus 79 is 25. So x, so 4x square is 50. So what is this side? This side is 5 root 2. Just what is the length of other medians? So I hope we just went through this formula. So suppose median through B, let's say median through B root 2B square 50 2B square, sorry, 100 plus 2C square 32 minus 81. 19 plus 32 root 51 by 2. And median through similarly we will use it 1 by 2 root of this 100 162 minus 60. This will be the longest median. Fine. This is semicircle, circle. I am avoiding it. Okay. Now, suppose somebody asks you a problem like this. Okay. In a right angle triangle, D and E trisect the hypotenuse. Okay. And this length is x. Okay. So we have to show that p square plus q square is 5x square. What we already know is that AB square is 9x square. Fine. Now how to proceed? It is very simple, I think. How do you write P? So when we say MAN, suppose this is this is M and this is n. So, m is x, n is 2x. So, m a n, m a n plus d, which is a d square. So, it is b m b. Okay. So, a c square b m b, b m b is b m b, a c square into x, c n c. So, this is a b square into 2x. So, what do you have? 6x square plus p square is ac square plus 2ab square. Similarly, if you are able to see, what you are going to get again is 6x square plus q square will be ab square plus 2 ac square. If you simply add them, what you are going to get is 12x square is 3 ab square 9x 27. So, will it be 2x into x into 3x? 3, where did this 3? 3 भी तो यहाँ आएगा ना यार 3. Okay, so this is now 27x square. So p square is 5x square. Okay, so these type of questions you can get in IOQM, p square plus q square by x square is. I am not saying that this would be the only theorem, otherwise people what do? They may draw altitude. So basically what you will get involved into, you will get involved into proving the theorem as such. Okay, so remembering Stewart's theorem is of great help. Just as you can see, you found out the length of medians, you found out the relation between length of angle bisector. So if you want to find length of angle bisector, I think these students can very easily be found out, because this is the ratio known to us. So length of median, any other process would be more demanding. Apollonius theorem would be of great help. So Stewart's theorem does has a wide variety of uses in length chasing. In length chasing, it is of great help, because in length chasing we use either Pythagoras theorem. You can say that these things have been deduced from Pythagoras theorem. So that is definitely the case. But knowing the length of median is an asset. Knowing the expression for length of angle bisector, at least in terms of Mn, if not the final expression, is also an asset. And of course, questions where you are given a situation like this, okay, this median, this being median is just incidental. Any other case, we are able to counter it, we are able to settle it using Stewart's theorem only. Okay, so please be well versed, solve questions from say assignments or Pathfinder book of Prashant Jain sir, so that you are able to fathom what can be asked and you are able to very comprehensively grasp what sort of different situations you will encounter in this. I have taken some examples. As we move on, once we are through with circles, you will see that it is really, geometry will really explode very beautifully. Okay, now at this juncture, because we are doing it very systematically, we are confining ourselves. We are confining ourselves to the sequence that we are following. We are not randomly taking things. Okay. Now, what does Ceva's theorem says? That if you take any point and you draw lines like this, say, so what does it say? Suppose they meet at O. BD by CD, this ratio just we complete the whole path. CE by CA, sorry, EA, and then AF by FB is 1. Ratios we are deliberately taking as positive, even if the point is outside, suppose, okay, and we have a situation like this. Now, in terms of, we have drawn only when point is inside, point could be outside also, okay. So, in fact, similar triangles can be used, or half base into height can be used in proving this. I am using, say, area ratio. So, BD upon CD is area of triangle ABD upon area of triangle ACD. Same height, so it will be in the ratio of bases, is also equal to area of triangle BOD upon area of triangle COD. So, if you subtract it, ABD minus BOD, this is area of triangle AOB upon area of triangle ACD CO AOC. Now, CE upon CA, CE upon CA you can similarly say is just as we said area of triangle AOB. So, from similarly C you can say it is area of triangle BOC, area of triangle AOB, isn't it? AOB, yes, and then AF upon FB, AF upon FB, the area of triangle AOC upon area of triangle BOC. So, 1, 2, 3, you can multiply, you can see. Okay, so this is the proof of Ceva. I have even some of the theorems which I didn't prove, I deliberately skipped some of the proofs in our earlier class, and I specifically told you that please prove them, and if you have any issues then you can get back to us, but don't just remember things as a result, always try to prove them. Take your time, even if it takes half an hour, 30 minutes to establish the theorem, but that effort will bear fruit as we move on in actual problem solving. When you solve problems of actual that have actually appeared in examinations, you say somebody may even ask you find ratio of area of these two triangles. In that case, if we have gone through this, we know it is the same thing. So, this is the final result that we get, but the process in between, that gives you the hint of how to proceed in different problems. Now, the converse of theorem is the same. Converse of is that if BD by CD into CE by EA into AF by FB is 1, then AD, BE, CF are concurrent. Okay, this is of great help in proving the concurrency of medians, altitudes, angle bisectors. How? Or even perpendicular bisectors. So, perpendicular bisectors are will not be there because it is not passing through the vertex. Sorry, so BD by CD. How do we prove it? The converse part, we say let AD and BE meet at O. Okay, let me write it down formally. Let AD and BE meet at O and CO meets AB at F dash. Okay. So, by Ceva's theorem, what we have? BD by CD AF dash now we already know what is given to us is therefore what we have is AF dash upon BF dash is equal to AF by FB. So, what does this gives you? Just add 1, AF dash plus BF dash, AB upon BF dash is AB upon BF. So, you have BF dash is BF. And since F lies on AB, this implies F dash coincides with F. So, converse also holds, that if the product of this ratio is 1, then the 3 lines, we say the 3 Cevians are concurrent. These are called Cevians. AD, BE, CF, they are called Cevians, are concurrent. So, if you want to prove, say, medians are concurrent, in fact, initially, if you recall, we just took it for granted initially that they are concurrent. There are various ways. This is a fantastic way to prove it. One upon one, one upon one, one upon one. It is very trivial. In case of angle bisectors, I think it is very easy to observe in the case of median, I think. So, I have not In case of angle bisectors, we already know the ratio. BD upon CD is BD upon CD. We know it is AB upon AC, CE upon EA. And AF upon BF is AC upon AF BC. Multiplied, you get it as 1. So, hence they are concurrent. What angle bisectors are concurrent. In altitudes also, you can similarly say that they are concurrent, but in that case you need to know the ratio. Okay, fine. So, I hope you are getting it what we are into. Okay, so the very standard things are solved using Ceva's theorems. This is a very common question that is asked. Okay, suppose this is 6, this is 5, and so this is 8, and you are given, suppose you draw AD, this is 3, this is 5, then you draw BE, okay, this is 2, this is 3, they meet at O, and the question asked is CO meets at F. So AF, what is AF? This is a very common question. Once we have seen what the situation is, you can very easily say 5 upon 3 into 2 upon 5, okay, into, say this is x, so this is 6 minus x, into x upon 6 minus x is 1. That's it. So, this completes the problem. 2x if somebody is asking you the length of CF, okay, somebody is asking you the length of CF, then what we have? Stewart's theorem. Okay, somebody may ask you AF, somebody may ask you CF. So, if you want to find CF or BE, anything, then we have Stewart's theorem. Otherwise, this is Ceva's theorem. So, what you are able to, I think you should be able to grasp is that we have to see how they are applied in actual problems that we get in the examination, and for that I am again insisting that if you are able to, if you are confident that as and when needed you are able to prove it, then only you will be able to solve it in the solve the problem. That means you are able to use it because you know the steps prior to the final results. Now, suppose I say what is the area of triangle AOB upon area of triangle AOC, you can say it is 5:3, because you have gone through that process. It is not that you can remember everything, but if you have gone through the processes, you are able to recall how do you initiate problems. That is the crux of competitive exams, that instead of finding corollaries to the theorems, corollaries to the standard result, they go backwards. How did we get to those theorems? Do you know those steps? So, therefore, probably for the nth time I am saying that if you are able to recall the theorems, not only the theorems but also how did you prove them, that is the real asset that you will possess rather than the final formula itself. Okay. Let me also share with you Menelaus theorem. So, if suppose you draw a transversal which cuts the three sides. Okay. So, and say, let me use a different color. Again देखिए D E F. So, a transversal intersecting the three sides. So, again BD by CD into CE into AF by BF. This algebraically we say is -1 because you can see two of the ratios are internal and one ratio is external, or all three can be external. Okay. Suppose this is the line. So, all the three ratios can be external. All three cannot be internal. In such Cevians, we deliberately say positive because suppose this is the situation. So, what you get is that two of the ratios are external. So, two are negative and one is positive. Okay, so product will in effect be positive, even though in length we rarely use the sign of plus minus, but if you algebraically proceed external division negative, internal division positive, then you can see this is the situation that Ceva's theorem, Cevians, either two of them will meet the sides externally and one internally, or all three are internal. Here either all three are external or one is external. So, algebraically it will be -1. In terms of proving it, what we do is that we draw a line parallel to the base and say this is P. Okay. Now, can you see these two triangles are similar? Okay. So, BD upon AP. So, BD upon AP. What is it? BD. So, it is BF upon AF because the triangles are similar. Okay, this is parallel. We have drawn a line parallel to the base. These two triangles are similar. These two triangles are similar. So, what will you have? You will have AP upon CD. See, these two are similar triangles, APE, CDE. So, AP upon CD, what will it be? AE upon C. So, if you multiply, what do you get? BD by CD is BD by CD into CE by EA into AF by BF is 1. We have taken the absolute values. We have taken this. We have not taken the sensed distances. We have not catered to. See, if this is how you measure AP, then this will be negative. So that is why in length generally in geometry we confine ourselves to positive things only, but algebraically internal division is positive, external is negative. So that is how you factor in those things. Okay, a transversal cutting like this. Again, you can see it is a simple application, not a simple, not necessarily very simple, but again I would say a reasonable application of similarity of triangles. So I deliberately skipped it. In the previous lecture I told you about quadrilaterals primarily, so that there is a sense of maturity when you come across these theorems. I could have very well gone into from triangle, these are theorems related to triangles only. Okay, theorems related to quadrilaterals also, some of them we discussed, that the quadrilateral formed by midpoints of sides of a quadrilateral is always a parallelogram. We also went through what is a trapezium, what is an isosceles trapezium and stuff like that. Okay. So this is Menelaus theorem. So again, whenever you are asked something like this, a line cutting sides of a triangle at 3 points, Menelaus theorem is at your disposal to dwell into those issues. I would say Stewart theorem is very useful. You can see from Stewart theorem we went to Apollonius theorem, which was also you can say that helped us in determining the length of median. Always advisable to remember the length of the medians. Okay. Now let us solve some problems. Suppose you are given a triangle ABC. So this is length 6, 6, 8, 10. And let me draw a line. Say D, E, F. So this is 4, this is 6. Okay. This is say 2. Okay, this is 1. This is 5. And this is X. Suppose we have to find X. And then we can use Stewart's theorem to say find the sides. Okay, find X and AD. So how will you find X? I think that is pretty easy. Okay, AF upon BF, 4 upon 6 into BD upon CD, BD upon CD into CE upon EA. Okay, so this is 2, 3, 8 plus X upon X 15 upon 2, isn't it? So 16 x is 16 by 13. Now somebody may ask, just as I told you, somebody is asking you to find length AD. So we can apply Stewart's theorem. We have to find length AD. We know AC, we know AD. So this is something that we need to find. So what is the formula? So by Stewart's theorem, what will you do? M-A-N, M-A-N. So 8 104 plus 16, 120 by 13. AD square, okay, man plus dad, A D square. What is AD square? This is A. What is D square? 36. Man plus dad is BMB, okay. So B is something that we have to find. AD, M, 8 into AD square plus C and C. So C is 10, okay. So C and C, 16 by 13 into 100. C and C, isn't it? C and C. So 8 2 15. Okay. Now you can find AD square, collect terms at one place and determine it. Okay. So somebody may find you this. So Menelaus theorem, Stewart's theorem, Ceva's theorem, Stewart's theorem. So Stewart's theorem is very versatile. Please give special treatment to it. Okay. Because in length we don't have much, barring Pythagoras, similarity and congruency, we don't have much theorems. As we move on, once we go through circles, you will see that there are a lot of theorems regarding angles. But in terms of length, there are few. So we, as and when needed, we must stick to these 3-4 standard principles. In examinations, they generally don't go beyond it. Okay, now moving ahead, let me recap some of the things, and let me recap the notions that we did in the previous lecture also regarding quadrilaterals, and some questions regarding that also. Now somebody says, okay, just 1 or 2 questions at this fag end. Okay, now somebody says you take an isosceles trapezium. And what you do is that you draw its diagonals. Now if we take midpoints of the diagonals and parallel sides, and join this. What is PQRS? Parallelogram or rhombus, rectangle, what will it be? Okay, so by midpoint theorem, you can say in triangle ACD, PQ is half AD. In triangle ABD, RS is half AD. So these two are equal. Okay, let me say these two are equal. Similarly, here you can say QR is half of BC and PS is again half of PC. So you can say all the four sides of this quadrilateral are equal. This will be a rhombus. Otherwise, it would have been, see, in any case, it would have been a parallelogram. Okay, in any case, it would have been a parallelogram. It is rhombus because this is an isosceles trapezium. Okay. Similarly, say suppose somebody says in a parallelogram, just one or two questions for practice I am taking, not much time is left. Suppose we draw angle bisectors. What is the figure that they are forming? So I think you can understand, if this is theta, this is pi by 2 minus theta. So this is 90. Similarly, all the angles are 90. So diagonals of a parallel, okay, angle bisectors, very sorry, angle bisectors of a parallelogram. What do they form? They form a rectangle, isn't it? Suppose this is a rectangle. So angle bisectors 45, 45, what will this be? Here it is a rectangle, what will this be? ABCD is a rectangle. Definitely it will be a rectangle. Is it a square? See, these are angle bisectors. See, diagonals of a rectangle, they do not bisect this angle, okay? These two angles are not equal, these two sides are unequal. In case of square, they will all coincide at a point. Angle bisector is as good as the diagonal, but here that is not the case. So definitely it will be rectangle. Will it be a square? Will it be a square? This PQRS. Okay, just give it a thought. This is where we are ending today's lecture. Okay, so Stewart's theorem, Apollonius theorem, Ceva's theorem, Menelaus theorem, these are the theorems that we have tackled today. Most of the things regarding to triangles and quadrilaterals are over. Areas we have also catered to on most occasions. We will now in our next class be moving to circles followed by angles. Okay. So I hope this lecture would have been of help to you, and now we have come to a stage where we will be taking up, after going through all the theorems, we will be taking up the problems of the nature. Some of the problems we have taken up, it's not that we are not up to it, but after we have gone through everything now, we are actually free from the shackles, because we are doing it in a systematic manner. We are constraining ourselves to solve problems only about things that we have gone through in previous classes or in this class. As we move on, you see that we keep on adding and it gets accumulated, and we get really beautiful problems which lead us to explore this beautiful geometry. Apart from learning it from the point of view of examination, it is really a very fascinating thing, but you cannot learn it unless you solve problems on your own. Just listening to things, just seeing what others are doing, whether he or she is your teacher or your mentor or your friend, unless you pen it down, unless you put in efforts of your own, it will be difficult, or I would say it will be impossible to grasp the real chapter. So please do practice enough problems so that you are able to very easily recall what you have gone through, and then as we move on, you are able to incorporate the previous things as well as the present things in solving problems. Okay. So thank you very much. See you again.